Welcome back. This will be the lecture that's on YouTube, so hi YouTube, like and subscribe, something like that. What you missed, what we haven't done in a while is actually teach content. There was the exam last week, and then the week before that I was out of town that I had assigned a little bit of Lisa's content, Lisa being the person who taught this class last, with her permission. And item response theory is where that is covering. And then polynomous item response theory is what I'm going to add on today. So let me give you my plan for the semester, including homework. Okay? Number one, homework this week is fix your exam, right? It's due next week. We will have another homework assignment administered next week, which will be doing a factor analysis, psychometric analysis on your data, right? This will begin the your data portion of the class. That assignment will be administered, we'll give it out next week, which is the 12th. I'm going to put a due date for it probably the very beginning of the week after Thanksgiving. It's like a Monday, something along those lines. Mainly because I want to get that graded, give it back to you with my comments, and then allow you to use that, fix the comments on it, or to be your presentation on the last day of class. But that's it. That's the three assignments. One, the current one, which is fix your exam. Two, a homework assignment that will be on your own data. And then three, which will be the presentation, the final day of class, which will be your fixing any problems with the homework for your data. So three, yes? No, just the present. No. It'll just be the presentation. I just expect I'd rather than correct whatever the issue was, if you work with me to address it, if you don't understand or you do address it, that'll be sufficient. So, that work? I mean, I figure like 2 passes over, it should be okay. It will not be, by then, why I'm structuring it this way is I really I'm doing presentations for you because I want each of you to see, I feel like there's learning and seeing people do this in different contexts. And by doing the homework first and allowing me to give you some feedback on it, those presentations get a little bit more refined, right? And so that way, if there's a big problem, you can fix it. You'll have about 9 days or 10 days or 9 days to make the presentation and make a few changes. But that's the plan. Does that answer your question? And the motivation, okay? Reasonable? Hope so. I just feel like got to motivate what we do in here. So that's the plan for homework. So plan accordingly. When it comes to reading assessments, there's not going to be a reading assessment next week. Next week we'll have a guest lecture, I think. Right? Yes. Guest lecture for part of the class, which may be even more than you bargained for, but that'll be fine. It'll be somewhat thematic, a little bit thematic. But then at the end of that, I will have a lecture and a half before Thanksgiving break, 1 lecture afterwards, and then presentation day. So that's how it works. And at the end of your presentations, you walk out of here and you're done. There's nothing else hanging over your head, okay? That's good for me too, because when I walk out of here, I'm going to be packing, but yes. Okay, so on that note, what is today going to be? I don't know how much you remember about IRT. I assume you watch the videos, but I'm going to do my summary of IRT. And then I'm going to get into the lecture slides for the next part of it. And the difference between what you had watched and what I'm doing today is the type of data. So I'm going to try to make this a quick, there will be lots of slides I'm not covering. It'll be a quick summary of each. And I'll start with, I might start with these slides right here. Actually, let me do this. I'll start with some of the slides to begin with, but I may end up doing a lot of handwriting and giving you lecture that's just out of my brain, depending on how things go. Okay. Any questions? Any comments? Okay. Let's get this thing started then. And remembering, that thing is really annoying. I understand. I'm just going to keep the slides like this. Can you all see them okay? All right, because if I switch it to presentation mode, my OBS doesn't record the right screen. And I guess I could do kiosk mode real quick here. Or individual. There we go. Let's try that. There we go. That looks a little better. Okay, so I'm going to talk a little bit about how this sets up pretty quickly. And we're in the measurement part of the course. So remember, in structural equation modeling, we started with path analysis, where we assumed everything was an observed variable. And then we switched over and said, but what if you don't have an observed variable? We went to factor analysis, where we said, this is a latent variable, a latent construct. We're going to define it by a set of observable pieces of data, usually test items, questions, survey responses, etc. We estimated a latent variable from that. And then the structural equation modeling beauty is once we have that latent variable, it just goes in the path model like everything else would, as if it were observed. And although it's all done through simultaneous estimation, it's not a two-stage process. So for us, we're going to finish off the latent trait part of it. Up to this point, our data have all been assumed to be continuous, right? And we talked a little bit about that problem before. We said, okay, most of the time when we see data for this version of a class in a social or educational science, the input data are usually like Likert items, categorical test item responses, right? And we talked about, okay, if you have enough of those, if you have 5 to 7 or more, and the data seem to be mostly unimodal and unskewed, yeah, what we're doing up to this point mathematically seems to make sense. But in practice, that's seldom the case, right? We are taking categorical data and treating it as continuous. Now, let me see a show of hands. There is a class that Lisa Hoffman teaches, generalized. How many of you have taken that? A handful. Okay, so I'm going to teach this for people who may not have taken that class as well, but both. If you've taken that class, what you realize is that class said, okay, remember linear regression? We're predicting a continuous outcome. What happens if we have a binary outcome, first of all, right? Well, we have to switch how we predict it. We have to go and predict its mean. Well, its mean is a probability. We've got to move that probability from the range of 0 to 1 onto a real number line. It's called the link function, right? And then we predict that with a logistic regression or a probe regression. That's what IRT is to factor analysis, right? Confirmatory factor analysis is linear regression. Item response theory is the word we usually talk about for logistic regression or multi-category, multinomial regression, right? But what the difference is between the two is simply your data, right? So I always like to think about this from the perspective of, I'm going to give a very bad example. You're going to wonder why I took the time to do this. But I have to do this because I'm just trying to be true to myself, There it is. Okay. So let's imagine a factor model, shall we? Remember the equation for one item in a factor model. We have an item. I'll get there, I promise. Oh, 0%. Okay, we have an item Y for a person, and item that is one response. It'll take a couple seconds. My pencil will be charged. It'll be no big deal. It'll be no big deal. I'll just, when in doubt, use your fingertip. All right. That's right, YouTube. I'm so multi-talented today, despite the fact I'm making errors left and right on technology, and nothing wants to be the right size. Okay, so this is one item, one of those Likert items, let's say, in your factor analysis. What's the equation if you have one factor that it loads onto? Do you remember the equation for it? The intercept. We have our intercept. We have enough. No. Have our intercept mu. You know what? I got a better idea. Give me a second. Nope. It's coming, I promise. It's like, which way am I going to make equations with today? All right, we're going to go in LaTeX with Markdown. All right, this is Obsidian. If you're looking for a Markdown app, Obsidian is amazing if you like code. Anyway, all right, we can do a little LaTeX here. Y for a person and item is equal to, we have an item intercept. Mu for the item. Uh-oh, took the $sign off. Equals mu for the item plus a factor loading for the item times a factor score for the person that we don't observe plus some error that's considered for the person and item itself. So this is the residual term, the term that's not observed, right? So this looks like a factor model to you, right? How are we doing? All right, so here's how I want you to think about this. I can try. That is as big as it gets. 3%. Let's see if it works. All right, going back to Scribble. Okay, it's all this for an example. You're going to say, really, you did all this for this example? Yes, I did all this for this example because, patience for me. I don't know. This has been my life this week for technology. Here we go. All right. Come on, pencil. You are supposed to be a pencil. All right. Y for the person and the item equals item intercept plus factor loading times factor score plus error for the person item. That look better? You can see it better? I realize I'm on an angle here. Oh, well. Okay. So here's how I want you to think about this. All right. Where's the theory part of this model? Where does theory go? Now, that's a weird part. I'm going to do this. This side over here is data, right? Right? And you're trying to map your theory. By theory, I mean your assumptions about what the model happens to be. In our case, for a measurement model, you're assuming all these items measure the same thing. That's your theory. So the right-hand side is your theory. The left-hand side is your data. So if I were to change this around slightly and create, instead of a linear model, but I were to do a logistic regression here, what we would talk about is the natural log of the probability that y for a person and item equals 1 over 1 minus the probability for that same thing equals mu sub I plus lambda sub I factor plus error person item. Okay, this thing right here, now what you see here is the right-hand side has not changed. The theory has not changed, right? But the data have. And that's how to think about generalized modeling, generalized data analysis itself, right? Your theory, you're putting together a model on the right-hand side that is based on your theory, your hypotheses, or otherwise. That's what I'm calling theory in this case. But on the left-hand side, the data come in different forms, right? Should your theory change? Should the item measure the factor any differently or measure any different other factor just because it's binary versus polytomous or continuous? It shouldn't. So that's the idea of generalized modeling. So what we're getting into with the distinction between item response theory and factor analysis is, like I was mentioning before, the distinction between linear regression and logistic regression. But then you can go beyond that, right? What happens if instead, by the way, this thing over on, anybody want to tell me what this thing is called right here? A logit, right? The log of the odds. That's what Lisa Hoffman likes to say. Oh boy. Yes, yes, yes. Are you aware there are other ways of doing this? So basically all this thing over here it's doing is saying this probability of yi equals 1, that is what we would call the expected value of y, right? By expected value, we mean its mean. And in linear regression, if you remember linear regression, if I just go up the page here, in linear regression here, what is the mean? Right here is the expected value, right? And so what we mean by that is in linear regression, if you had, a bunch of data points or something like this, and you have a regression line, that regression line itself is the expected value of y for value of x, right? So here, if x is 2, and this is, 4, right here, you would say on average, in all the people of average of all the people who scored 2, their y should be equal to 4 on average, right? But we know it's not, a mean is not perfect. Actually, I should probably, I'm trying to draw a normal distribution here. All right, there's a sideway, a conditional normal distribution. All right, so what we know is that the regression line is going through all the means of the conditional normal distributions of our data. So what happens here is we're just still doing the same thing. We're still modeling the mean of our data, but because the mean in categorical data is going to be between 0 and 1, inclusive of the ends, right? We have to transform it. Now, we're not transforming data, right? We can't transform our data because if you plug in just y instead of the probability of y is either 0 or 1 here. That means the numerator is either going to be a 0 or a 1, and the denominator is either going to be a 1 or a 0. But when it's 0, you can't do that, right? You can't divide by 0. I shouldn't say you can't. More technically, it's undefined, which is funny to me. It's like we've had how many eons of math, and yet we still haven't defined it? I mean, anyway, no, I'm just kidding. We have a good idea of what happens to it as the denominator goes to 0, certainly, right? Okay, so this thing is us taking a transformation of the mean to map the mean from 0 to 1 onto the space of the real number line, right? From negative infinity to positive infinity, right? Because once this is on the real number line, then the regression equation looks sort of the same. Although I did make one little error on this. I left error on here. We often take the error off. So that's how it all connects. And that's what we're going to do. Questions on anything that I just showed? All right. So that's this right here. The actual data, link function. This is what I call theory over there. And you know we can't predict. This is what happens if we don't use some type of link function, right? So on the left-hand side, this is a linear regression applied to the mean of binary data. On the right-hand side, that is our link transformed, right? So when we go and untransform it back to a probability, right? Not a logit, or not a log, not a continuous number. We bound our prediction in between the upper and lower limits, which is good. That's what we want to do. All right. So the thing that we just called the logit is called a link function right here, right? This is called the log odds, the logit. I hate the word logit, but, I think, that's how it goes. Logits, if you haven't worked with logits before, in this course for measurement models, this really makes sense. Is important because a lot of our ranges of parameter values are going to be anchored by where 0 is in a logit sense, right? So if you're predicting a person has a 50-50 chance, let's imagine binary item response. Imagine those items on your test. Did you get them correct? Did you get them incorrect, right? We're going to model the probability someone gets it correct as a function of your latent ability. If that probability is 0.5, the logit is 0, right? But as you can see, the logit runs out of numbers pretty quickly. So once you get up to a logit of 2.2, that corresponds to a probability of 0.9. But the flip of that, the converse, if you take -2, it's the converse or the complement of 0.9. So whatever 1 minus the other number would be, in this case 0.1, gives you the negative value of the logit. So logits are somewhat reflected right here about, right? Furthermore, if you think about extreme values, a logit of 4.6 corresponds to a probability of 0.99. So what that means is if you think about it, let's imagine we're doing our factor analysis, but applied in logits, right? If you get an item intercept parameter, in factor analysis, the item intercept parameter, if you have a standardized factor, should be the mean of the item responses for that item, right? In item response theory, but then not only is it the mean of the responses to the item, what is it? How do we interpret the intercept? We interpret the intercept as being the expected score when someone's factor is equal to 0. Instead, for the logit, we'd still say the logit, the intercept will be the expected logit for someone who's correct or whose factor is equal to 0. Same thing. But now, if that logit, that intercept is 4.5, what's that tell you about the item? The average student is going to have an almost certain chance of answering the item correct. Right? So that scale, what I'm trying to get at, is logits or probits or these links have a bit of a metric baked in. Right? They're a different metric than what you're used to with raw data. And with raw data, we talked about that is factor analysis, right? The slope in factor analysis, right here, lambda is in units of y per units of the factor in factor analysis. I can't get this to move away. Go away. There we go. Units of y per units of the factor, just like a regression weight, units of y per units of x. In item response theory, though, when we get to the logit, this slope is now logits of y per units of x, right? So that means how much logits change. That's different than units of y, right? Do you see the distinction? And that is why I want to come back to here, because if your slope is like, if your factor loading is like 1.2, what's that mean? That means for every 1 unit increase in theta, or your ability, your latent variable, your logit's going up by 1.2. Well, that's great, but if the intercept was 4.5 to begin with, you're saying that a person who's 1 standard deviation higher on the latent variable now is 4.5 plus 1.2, or 6.2 logits, but the actual change in probabilities goes from like 0.98 to 0.999, something like that. Right? It's a small change. So what I'm saying that for is because of this nonlinearity, when we think about logits still work the same as linear models, but when nobody wants to talk in logits, nobody wants to talk in the other version of this, probits. They'd rather talk in probabilities. Those probabilities end up, where you're at on the logit scale ends up describing the impact of it. For those of you who are familiar with this, that's why whenever we look at categorical data analyses, we often do things in terms of effect size, and we quantify it in terms of odds ratios, right? That would make a difference as well, too. Anyway, questions on any of this? How are we doing? Okay. Sounds like we're doing fine. Let me just keep moving on. How it works is this, though. In normal theory, logistic regression or factor analysis, we assume the data follows some type of normal or conditionally normal distribution, where here, mu on our normal distribution is defined by our model for the means, at least we'd call it, right? In the factor analysis case, that is the part in the bracket right here, right there. Whereas now, when we have binary data, we use a different type of distribution altogether. Right? It cannot be normal. Right? The data only have 2 categories. So we use a discrete distribution. The letters PDF in the continuous case stands for probability density function. We use that sometimes for discrete distributions. Sometimes you also see some other term called the probability mass function, just really denoting that in a discrete distribution, the height of the y-axis is in probability, whereas in a continuous distribution, the height on the y-axis is like a relative frequency. Right? Probabilities are inherently interpretable. Relative frequencies are hard to interpret. Right? So that's the one distinction before it. But the key in all this is saying, oh, our data aren't continuous, then what are they? Oh, they're categorical, they're binary. What distribution describes the sort of variation in a binary data sense? The distribution we use is something called Bernoulli. Bernoulli, help me out, if those of you who do math, you know much about Bernoulli? Roulette wheel, right? Probability?
Yeah.
Maybe I'm wrong about that. I was thinking I think Bernoulli was heavily tied to gambling back in the 1600s, I want to say. Yeah. I say when you see statisticians' names that are old, you got to think they come from usually gambling, sometimes alcohol. That's where statistics gets its foundation. Are there outlets? I didn't realize. Well, even better. Now this is even getting better. All right. So Bernoulli is a distribution for categorical binary data. So before we said, instead of using mu here in this distribution, we're going to substitute our model. For the Bernoulli distribution, P is the expected value, right? In the normal distribution, the expected value is mu. So P, stands for the probability. How the Bernoulli distribution works, there's one parameter, it's a probability. It describes the probability of a 1, right? So if y can either be 0 or 1, when y is 1, the probability of a 1 is p, that probability. When y is 0, the probability of 1 is 1 minus p, the complement of that probability, right? So now a Bernoulli distribution still has a mean, and that's where the link function comes in. Because all of our parameters are defined on real number lines, we want our thing we're predicting to be also defined on a real number line. And what this ends up looking like is the following. Let's see if I can get this a little better here. Okay, so here what we're saying is p to the y times 1 minus p to the 1 minus y, that's our Bernoulli. But p really, right here, is our probability. So we need to take our logit of p and back translate it, right? Because logit of p, right here, this is our logit. It's continuous, but p itself has to be in between 0 and 1. So this is where we come up with a different function that you're probably more familiar with, which is something called the inverse logit, right here, right? E, Euler's constant, raised to that logit value over 1 plus e to that logit value. That is what we see. So that's how we actually don't transform our data. What we'll end up doing is transforming the mean. If we think of this as our likelihood function for one case, and we talked about building likelihood functions earlier in class, we have to build it across all the cases. Now we can express our likelihood function as a function of our parameters and our data specifically, and life is good. However, life is somewhat good. There's a little bit of problems with what we do, but that's the idea. How are we doing so far? So similarly, what if we don't have 2 categories? What if we have 3 categories? What would we look for? What's that?
I said
Punt. Punt. No. Jonathan is no help. Not these days, it feels like. The idea, if we have 3 categories, is the same. What distributions accommodate 3 category data? Right? And we go find that distribution. I'm not going to tell you the name of, actually, I'll tell you the name of it because it's coming up. Distribution is sometimes called multinomial or a categorical. The difference between the two, a Bernoulli is a one-trial binomial distribution. Remember, binomial being the distribution where a number of successes out of number of trials. This is a one-trial version of it. The multinomial is the number of categories drawn out of a number of trials. Instead of having just a success or a failure per trial, you might have, like rolling a 6-sided die, number 1, 2, 3, 4, 5, 6. Right? The multinomial describes the probability of any one of those categories out of a number of trials. And a one-trial multinomial is sometimes called a categorical distribution. Right? So categorical and Bernoulli sometimes get used. You do sometimes see binomial or multinomial. But just realize they're always one trial, that one trial being that one observation of the response. But the process is this. We find a distribution. We figure out its mean. We apply a link function. And we estimate our model. The link function and the estimation is applied in the estimation part. Right? So what if we have count data? Count data is different than completely continuous. in that this includes negative values and non-integer values. It's different than a multi-category version of this, a multinomial, because you can have infinite counts. It's also different than this in that a true zero means you did not observe any of the count. Whereas this, you may have a zero category, but it may just be a name or like a nominal sense, right? So when we have count data, we need a distribution that maps onto the sample space of integers where zero and positive numbers are included, right? And sort of an infinite number. Names for those go by Poisson, also negative binomial. And then, depending on, these right here are very complicated, let me start with. But Poisson and the count data make things look like kindergarten because there's all sorts of options. When you pick a Poisson, you assume the variance and the mean are equal, and that's seldom the case in data. You have to worry about under or over dispersion, and so you hear things like hurdle models or negative or zero inflated versions, zero inflated Poisson, zero inflated negative binomial. So the process is still the same, though. How are we doing? Right? Okay. The fun thing about all this and why this gets so out of place is the following. Most of our class we're teaching with the normal idea, the normal theory. But really, we shouldn't do that. The hard part about data is almost none of the data that we use in this class at this point fit the assumptions of continuous. And most SCM classes do it this way because the normal distribution is so easy, and I say that in quotes, is really able to be worked with. Like it has some really nice properties mathematically that we use it. And that's actually the reason why we get a whole model fit section that has RMSEA and we know what it means. Or what we understand about CFI, TLI, all the things that we think about. Oh, it gets easier to look at normalized residuals. You know, there's only one or two sets of residuals on the mean vector, residuals on the covariance matrix. Problem is, most of our data aren't normal and not even conditionally normal, right? So what we really should have been doing is teaching categorical the whole time, but this is a little bit harder to understand because it changes a whole lot when it comes to a little bit of model behavior. Model fit gets harder. Estimation gets ridiculously harder. And complicated and even more is that factor analysis largely grew out of psychology with some help from statistics and related fields. But a lot of the latent variable modeling on binary data started in education and then sort of branched into psychology, but the psychology branch came after factor analysis. So you have a bunch of different terminologies as well too. So that's part of our issue. So let me move forward here. Let's get to the following. There are other link functions for binary data. So I'm going to go back to just the idea of 0 and 1 data for right now. The logit link is what we just talked about before. Turns out there's another one called the probit. The probit is where we take basically our mean value of y, that mean probability, and we turn it into effectively a z-score. Basically, what is the value of the z-score where the area under the curve to the left-hand side, my right, your left, happens to be, right? So if you remember in basic stats, if you have a cumulative normal distribution right here, right? And this is the probability that some z is less than x right here. This is x, right? This right here, this probability would be your item response probability. You translate it down over here to the z value on the z-score, and that is actually the probability that x is less than z. I totally screwed up my notation there. All right. Probability some value of x is less than the value of z right here. Right? This is the probit function. It's technically like an integral. You get it from an integral. There's ways of approximating it quickly. But basically, we're working on z-scores there. The big difference between probit and logit is sort of an assumption about how much variation there is on hypothetical values that don't exist. What happens in a Bernoulli distribution? Actually, I should say that first. You'll note here one big difference between Bernoulli distribution, which is where we're going for binary data, and continuous normal distribution, is that the normal distribution has two parameters that describe it, a mean and a variance, but the Bernoulli only has one. And when the Bernoulli only has one, the variance for Bernoulli turns out is a function of the mean. The variance is p times 1 minus p. So when you think of it that way, what ends up happening is we don't have a real obvious space where error variance shows up, right? Because error variance we characterize with sigma squared. But in the Bernoulli, there's not a real easy way of seeing an error variance with respect to the data distribution, where p is on the scale of 0 to 1. When we do the link transformation, like we have here, I had sort of started by adding an error term here, right here, to it. That is true. There is one there, but we hardly ever talk about it because this error follows a logistic distribution. Have you ever heard of the logistic distribution before? Logistic distribution looks kind of like a normal distribution, but its parameters are fixed, they're constants. Yeah, it's the mean of it is 0 and the variance is pi squared over 3. That's some odd trivia for you. But this is the difference between Bernoulli and logit. In Bernoulli, that error is logistic. In logit, that error is logistic. But in probit, that same error is normal with a mean of 0 and a standard deviation of 1. So this is the logit value. This is the probit value over here.
So is that the same term information? That's what differentiates between probit and logit?
Well, that's not exactly, because the probit and logit have a different functional form, right? So turns out, if you were to look at both, if you were to superimpose them, if you were to take logit and rescale all the parameters, take probit and multiply all your parameters by 1.701, that was, I know that sounds crazy, but it gets even closer. The probabilities line up on top of each other. So the functional form differs, but also the assumption about variance differs. So what that sort of conspires to give you is slightly different estimates that should be equatable. You should be able to put them on the same scale with a different probability. Basically, that 1.7 changes it. Okay. That answer your question? Okay.
Yes, thank you.
Other questions? Okay. So moving through this a little more quickly here. Item response theory in psychology has a history of calling it item factor analysis, whereas item response theory in education is just called item response theory. By the way, the term item response theory sounds beautiful because I don't know you can get more general than that. What are you analyzing? Item responses. So yes, of course, this is a theory for it, presupposing it's the only theory for how people respond still. The idea is the following. There are sort of two differences you'll see out there between the two. Again, if we take logit, the probability of y pi equals 1 versus probit, right? I'll just call that right there. So in item factor analysis, we often see the linear equation is the same that we had previously. Sorry for the size of this. The linear predictor has an intercept and a factor loading. Okay? All right, so this is item factor analysis right here, we'll call this. Right? In item response theory, often this same logit right here but now it looks a little bit different. it goes by different parameters. Right there. So we get an A parameter, a B parameter, and a theta. So let's do some translation, shall we? First of all, between these two equations right here, the data are the same. So what we know, therefore, that these two equations should give us the same results, but just a little bit more transformed. So if we were to go and look at that, we could take equations mu sub I plus lambda I fp, and let's take a sub I beta p minus b sub I right here. Let's multiply a through to give us a linear equation that looks the same right here. Right? So if we have ai bi plus bi theta p, right? So now we're starting to see some similarities. Of course I can. Why? Wish I could just move this thing, but it's not movable. Can't hide it either. All right, how about I move my mouse over too? That'll work. Okay, we have 1 minute till break. First of all, theta is synonymous with F right here, right? So we can have AI BI plus BI times FP. Theta and F are different symbols for the same thing. They're the latent variable. In education, we often call theta an ability, so that from your assessment, that score represents a theta of your ability. From factor analysis, we often call this a factor, but they're the unobserved characteristic that we were trying to measure. So then, turns out, here we've got BI is equal to lambda I, and AI BI is equal to mu I, right? So now, this term, B, which we often, did I get that right? No, it's an A here. AI, and you know what that means? It's break time. Let me clean up my slides and make this mistake go away. How about 10 minutes? See you at 1:30 p.m. Central Time. All right, I think we're back, and I see my volume bar going. So back at it. What I was saying before break is if we multiply A through and rearrange terms a little bit, you want to work now, right here, right? So we multiply A through, then it's AI times BI plus AI times theta, which really means A is the factor loading. So here we would call this in factor analysis the factor loading. And in IRT, what would we call it? Item discrimination. Item discrimination is a absolutely terrible term. There are a whole lot of terms that could be changed in statistics, but item discrimination should be at the top. But item discrimination, why it's called that, is it describes, if you think of your ogive, right, your S-shaped curve, where if, oh my goodness. No, it literally was the one before. All right. If we have theta down here, and we have the probability of a correct response given theta on the y-axis, a very weakly discriminating item looks like this. That's a low discrimination. But what discrimination is characterizing is how fast that probability changes. So that basically the amount this item discriminates between low probability and high probability, right? So a high discriminating item, like the most discriminating item, would look like a step function, right? What I mean that is, below this part of the step, the probability is very low. Then above the step, it's very high, but that step itself is very narrow. Like it's not a very big step. That's why the term discrimination is there. Again, not a great term. But item discrimination and factor loadings are synonymous. So much so that when I teach sort of a class where we have to blend everything together, I will keep saying discrimination slash loading, right? Discrimination slash loading, because in so many ways, if you go to the wrong field and you say factor loading, people will be like, huh? And if you say, discrimination, people will also say the same, what? Right? So you have to sort of speak both languages. Similar to that, so A and lambda are the same. Now, it's a little bit different over here. we can do a little algebra and show that, right? Basically, bi is equal to the ratio of the item intercept to the factor loading for one item for a one factor item. This right here, mu, we know as the intercept, right? But B has a special term. It's called difficulty, right? And here, I'm going to flip back over to the slides to sort of describe these here. Item difficulty describes how much, so B, in the way that the IRT model is parameterized, if you go and look at this equation here, when theta equals B, what happens in this equation, right? Theta equals B, this part right here goes to 0, right? And if this goes to 0, that means A times 0 is 0. And the logit of 0 we just saw in my chart last time corresponds to probability of 0.5, right? So in that respect, B corresponds to the value of theta, where a person would have a 50-50 chance of responding with a 1 on that item, right? So the higher B gets, right, B goes up, the higher ability must be for a person to answer the item correctly. If we put this in the education context, right? The harder, more difficult an item is, the more ability it takes to have a 50-50 chance to answer it correctly, right? So difficulty is what's called the B param. Yeah.
Can you explain how, like, the idea of difficulty and discrimination? Well, how do those map onto like Likert scale?
Great question. Likert scales are a little bit different, and we'll be talking about that in the next hour. Let me identify these first, then we'll get to that, okay? Why I say that is there's more than one discrimination, or more than one difficulty, excuse me, for the models for Likert scales, okay? So let me get to difficulty first, then we'll do that. So when you see difficulty, you often want to do things like this. Play Pokemon. When life gets hard, play Pokemon. This is Lisa's example from last year, but here's how we think of things. And this year too. Oh, and generalized and clustered. So if you think of item difficulty, let's imagine I gave out a bunch of items and I said, can you identify this character in Pokemon? We often just order our items in front of this, right? Item difficulty would say, does anybody know who that is? Pikachu, good. That's about the level I am. And actually, I know this one. Anyone know that one? Snorlax, yeah.
In the video, Lisa actually puts you on blast and says, you know who the people are looking for.
I did. I don't know anymore. Gengar. Gengar. And who's this? Bidoof. Yeah, Bidoof. Yeah. Yeah, I've regressed in my ability. But so this is the interesting difference between the two different disciplines would really give us this information. Psychology, we never talked about this for fact analysis. But what would be the analogous parameter that would be difficulty? Be hard to tell, right? Well, if 0.5, there's no 0.5. I think that's the thing that holds you up, right? But intercept is similar to difficulty. Actually, it's the opposite scale, right? It's not the same, can't be the same, because the intercept means something different. Intercept is the expected value when the factor is 0. But as the intercept moves up, so does the difficulty. That happens in IRT as well, too. But IRT really, and the people who really developed IRT in education talked about this as something we call a construct map. Basically, when you have a certain score, what does that correspond to in terms of hard items? That doesn't mean you, like, if you gave me this, which I can't believe I got this right last year, but evidently I can't believe a lot of things. If I'm like that score, if you get that score, what does that mean you can do? That's what the construct map is really trying to tell you. So this is sort of saying how this works. So IRT really brought that about. We see this a lot in well, this is this is whether or not you can do certain types of tasks in a study of aging, right? Grooming yourself all the way to drug transfer or so forth, right? This is in terms of how hard these items are for elderly population. We could do the same thing with items on a math test. We could do the same things with items on that dreaded test in front of you right now, right? Which is order items by how hard they were and sort of describe where you are on that scale. That doesn't mean, for instance, that if your ability level is right here, it doesn't mean that everybody right there will answer that item with a 1, but that's sort of an ordering of difficulty for how it works. Am I getting through? Does that make sense? How are we doing? Okay, so that is the big thing. In IRT, there are different models, which is really crazy. Now I'm going to go step into the education branch of this lineage for a moment. In 1950, Frederick Lord came up with the 2-parameter normal ogive model, which is basically this parameterization right here, where the probit was used as a link function. Okay? And then shortly thereafter, in 1960, I am now blanking on the first name, but Roche created something called the Roche model, or the 1-parameter model. Now, if you're a true Roche person, now let me back up for a second. The 2-parameter version of the model, the one that we would most consider closest to what we've seen in factor analysis, didn't come out until 1968. It was probably before then. Actually, 1950 had 2 parameters too, so you'd have that. Those 2 parameters, this maps closest to what we know about from factor analysis. Basically, the item discrimination, the factor loading, etc. Going back, the Roche model itself constrains all of the item discriminations to be equal, all the loadings to be equal. Right? So here, when you do that, you get these parallel ogives. And it turns out why this model has some traction is there's some theoretical statistical properties that people like about this. That doesn't mean that it's really good for data, though. And this is the weird part of the education world. The theoretical statistical properties are this. The thing that people like is the item characteristic curves never cross. So items are always ordered by difficulty regardless of which level of the ability you're at, the latent variable you're at. Okay? Whereas if you have a 2-parameter, if your ability above 0, the dark purple line item is more difficult. The probability is lower. Whereas the pink has a higher probability. But you see, once you cross ability of 0, it's the reverse. Right? This is an easier item for low ability versus a harder item for the others, which is a weird quirk. We all admit that. However, so what that quirk does is it pushes a lot of people to really like the Roche model, this 1PL model. It's not quite Roche. And this group, I'm like choosing my words carefully because they're a bit of a cult. They're the closest thing to a cult we get in science, not for science, in my version of science. And here's why. They love the theory, but when theory meets data, it's seldom the case that theory fits. The model fit of a Roche model is really poor. If you look at Roche model from a model fit point of view, it's possible to build an exam where all the items do that. You're going to have to probably throw out a lot of items. Start with a lot to end up with a few to do this. Whereas, more practically speaking, the 2-parameter works. So I'm going to get away from the Roche model, but you're going to see that in places. You're also going to see another version, something called the 3-parameter model, which basically says, those curves, they don't need to asymptote at 0 for probability. There might be some lower bound probability where the asymptote falls. Sometimes we call that a guessing or a pseudo-guessing parameter. But those curves, this three-parameter model, guessing that parameter term really is an education term. So if you're not studying cognitive abilities, if you're taking a personality inventory, you're not guessing whether you pick option A or option B on a two-option forced choice item like an MMPI item would be. This thing is how do I want to say that? A three-parameter is, to me, this is also crazy because in the testing world, it's just large-scale academic testing in K-12, let's say, in education, you typically tend to see the three-parameter model or a one-parameter model. Like the two-parameter model doesn't seem to work there, whereas everything else that we do in research and science, often it just looks at the two-parameter version. So, not going to get a whole lot into these, but I will say this model, if you're thinking of this as guessing, for me, think of it as a lack of model fit, and also an index of that. Yeah.
If you were to try to create your own model image that occurred,
Mm-hmm.
would you have on the right-hand side like your guarantee like a 0.2 and that's fixed plus things, or
So you're saying what is
how
the
would I actually build
a
that?
two-parameter model? So you have the lower asymptote, which is the parameter, and then what's left over in the probability is 1 minus that. And so basically you're saying this right here was the probability from the two parameters, so it's how much of that what's left over once you consider the asymptote. Yeah.
I was not trying to
Oh, sorry.
get the weeds.
Yeah, yeah.
How do you do that in R or M plus or whatever to actually create the model that fits that has that fixed parameter
Oh,
and
you.
intercept?
So
Because I think it's a lot of the logistics you're
I
working
think I'm not understanding.
so
What are you trying to do first?
so how am I going to build my item characteristic curve
Mm-hmm.
so that it has a new intercept of 0.2 as opposed to
Ah, that's a great question. So 0.2 is not an intercept. So this is not an intercept. C is not an intercept, it's a lower asymptote. So it's a rescaling of all the other parameters. So what ends up happening with C, when you have a C parameter in your model, a couple things about that I didn't mention before that I need to mention now. Here you can see, take a look at the dark purple line here, right here. Turns out the B parameter is also at the point of inflection. The point of inflection being where the what is it? The derivative itself of the line tangent starts to reduce, right? The second derivative. You can do the second derivative test to figure out that is, right? It's the point of diminishing returns in probability there. When you add the C parameter to that, actually shifts the point of inflection up. So it rescales where it happens to be. The parameters are still the same, item discrimination, item difficulty, but they're estimated. They're all going to be yoked. They're going to be transformed. You cannot just add this parameter and expect these all to be the same. But yeah, so here, like for instance, item 4 and item 3, the two pink purple items here, these do have the same difficulty, but a different guessing parameter. And you see the shapes are different. So it sort of rescales the entire probability. Does that answer your question a little bit better? Okay, no problem. So you can also do a 4-parameter model. That would be an upper asymptote. Hey, there's a 5-parameter model I've seen out there. You can do a lot. Should you? I don't know. Think of it this way. If you're looking to if you're not in educational testing, how many of you would ever use this to go and estimate student scores? See, nobody. Excellent. You stick with a 2-parameter model and you're good. Okay? When you get into educational testing, people start worrying about this a whole lot more. Okay? So we're going to stick with a 2-parameter model because that's actually keeps us in Lavon. If you want to estimate a 3-parameter or even more crazy model, there's the MERT package. My previous time I taught this went through all that. You can go see that online, but it's not necessarily needed either. It turns out, so that's the models themselves. Everything I've shown you at this point are for one latent variable. But as you know, just like in CFA, we can generalize to more than one. So you have an item that measures 2 different traits, you can have that. Similar to CFA, when we talked about factor analysis before, we said, oh, but we need a way to identify where the mean of the latent variable and identify where the variance of the latent variable happen to be, because we can observe them. Those methods are still the same in item response theory. In the Embertson and Rees text, you typically see this sometimes called anchoring. I don't know that that's exactly it, but model identification is basically it. You remember in factor analysis how we could figure out the factor variance is either we set it to 1 or we set one of the item loadings to equal to 1 and estimated it. Same thing here. Same thing when it comes to the item difficulty. If we set one of the item difficulties to 0, then we can actually estimate the factor mean. Remember that factor mean now resembles or has a component of that first item's difficulty as well too. So it's the same. Same in terms of identification. Depending again on your use case for the model, the same choices of identification for you will be the same. What I'm trying to get off of this is the following. There's a lot of weird terms when it comes to binary data, but the process is so much the same. And when you get to Lavon, your model syntax doesn't change at all. At the very end of it, when you submit your request to estimate the model, you add a single command that says which items are binary or ordered categories. And then the output changes, so you have to be wary of what those output things are. But your choices, the process, everything else is the same. And then it turns out if you go into M+, if you wanted to get, M+ has a lot more distributions to use. So if you have count data, if you have sensor data, if you have continuous data, M+ can put all that in the same. And it also makes your syntax for the model is not changing. Certain quirks of the syntax are a little bit different if you're referring to a difficulty versus an intercept. But by and large, it's largely the same. So what I want you to think of is all that stuff you learned from factor analysis, so long as we do it this way, is about the same. Okay? And I say about, because I'm going to say why that is one last bit last, and then we're going to stay in this Lavon world. Okay? I should note, item response theory, if you want a deep dive into it for the educational testing version of it, our program offers that class in spring. And so why I say that is what I'm not covering in this class are things like how we develop a scale with item response theory. Turns out there's a characteristic, something called item information that says how much information an item has about a person. In item response theory, it's a function of the ability. So if you want to build a licensure exam, certain items will be different, more informative than others because you're going to maximize how much information you have right around where a cut point for someone being licensed to be a doctor or a nurse would be. So that doesn't get covered in what we're doing here. Similarly, if you have two different forms and you need to equate scores, that often falls into that type of a course as well. So I'm cutting out a whole bunch of item response theory in lieu of that other course. Also, if you don't have time in your schedule for it, or if you do and you want to compare and contrast, I have previous version of course notes for item response theory, which is a deep dive in that educational measurement version of it. You're welcome to them. Just send me an email. I'm happy to send them to you or point them to where those are as well. Okay? So what are we missing? We're missing the scale construction, why item response theory enables computerized adaptive assessments, all those things. We're going to focus on just how this is similar in the structural equation modeling world. Okay? Also, reliability is not the constant. That's actually a ramification of IRT as well. Item ability or reliability in factor analysis. Reliability is what we term. We mentioned this. We mentioned before coefficient alpha, Spearman-Brown, coefficient omega. You've seen those. We talked about that a little bit in the factor analysis unit. In item response theory, there is no one reliability. That's the thing to take from it. So where you'll see, people will report reliability in IRT, it's not a really good idea because reliability varies as a function of the latent variable. Meaning, if your theta is right at the average, if your latent variable is right at average, your reliability will be one number. But if you're on the tail of the test, to the ceiling or the floor, it will be another, right? What we're doing with the categorical data model is showing a little bit more relationship between where error is and the latent variable itself. So that gives rise to this idea of what we call item information, which is roughly reliability. It talks about how much information an item may have. In factor analysis, item-specific information is constant. It's the unstandardized loading over the error variance. I mentioned it briefly. I don't expect you to remember that. So in factor analysis, how you make your precision for your latent variable. How do I make my test variable? Basically, how do I increase reliability for someone's latent variable or score? You just need more items because items are all contribute the same to each theta. But in IRT models, reliability is really information over one, information plus one. Information itself, what you're saying is, wait a minute, information, what's this? Well, there's a concept we call item information, right? So in IRT, which is this graph on the left, I should just use my pointer here, it helps on YouTube. The graph on the left for IRT, these items give rise to the information curves that are seen right here. Item information is this function right here. And where that comes from, if you're really wanting to know, is what we're defining is a statistical quantity that's really important in like estimation almost. We're looking at what's called the Fisher's information for an item, which is defined in statistics as the second derivative, partial derivative of the log likelihood function with respect to the trait. Nobody has time for that. There's the formula right there. Okay, don't do derivatives unless you're, really like to. But what that means is it's discrimination squared times the probability of a correct response times the probability of an incorrect response. Both of these being conditional upon the value of the trait. Right. So as you can see, where your trait value is changes these product terms. Right. And so the information an item provides is curved. And what you'll see here is for the pink line, the bright pink line, item 4, I guess this is item 3, although it says item 4 up here. Well, let's do the pink. Do the pink line here, yeah. The pink line has a little bit more information than the dark purple line. The information is peaked roughly about the same place. When it comes to the dark purple line, that one, actually, these are all 2-parameter items. The information is exactly the same place. The peak of information for an item is at its item difficulty. So when you switch to IRT, you think, what makes an item good? It's most informative right about where its difficulty looks to be. Right? So that means these items, item 3 is really good at measuring people whose ability is right around 0. And item 4 is less good, but also right around 0. And if you were to draw the dark blue and the light blue lines over here, they would have a little bit different location. Their difficulty was -1, so their peaks would look almost identical in shape, but they'd be shifted down to -1. Right? So you're saying, all right, if I'm going to build myself an exam where I really want to make sure people have a minimum competency, right? I want to make sure people are better than 1 standard deviation below the mean. You would pick items like the blue ones to load that exam up with, for instance. But once you have all your item informations, you sum them up and you come up with something called the test information. Right? This is item information right here. Test information. It's the sum of all the item information. And this shape of this curve tells you where your test is most reliable. Right? So if you look at the blue line, it's most reliable somewhere between -1 and 1, something like this. Right? But think of it this way. This is the sum of all those items that we had before, all their information. If you're building an exam and you really want to focus on low performing or high performing, you would select different items from the same pool that would be on the low side or on the high side, and the shape of this would be different. So your reliability or precision would be it. But here's why I'm telling you about information. Because information, if we take 1 over the square root of information, we get our standard error or conditional standard error of measurement for that trait. Meaning a theta with a value of 1, if we took 1 over the square root of this information, its standard error would be right there on that red line. Okay? So what you can see is how precise we are at measuring the latent variable varies as a function of the test information, basically, right? And the places where the test is most informative, we're the most precise. So this gets into what test construction is. Again, that's IRT for the other time. For us, why I'm saying that is if reliability is defined as information over information plus 1, you can tell that reliability varies as a function of information. And what that means is one number to summarize reliability doesn't make sense. Does that make sense? Right? Really, what you see in item response theory, if you're talking about scale development with it, is not one reliability. You see conditional standard errors of measurement. That's what it's called. In fact, so much so that you go into, if you're into assessment, if you're into building scales, the American Psychological Association, the American Educational Research Association, and the National Council for Measurement on Measurement and Education, NCME, AERA, APA, those 3 organizations jointly publish something called the Standards for Psychological Assessments. Have you ever heard of this before? You may have. Anybody heard? How many of you have heard of it? The APA standards. Let me show this real quick to you. This is a very heavily edited volume. You can see this is the APA website where it comes here. But this is basically the guidelines. If you're building psychological scales, you go here for how best practices and guidelines on how to build it. In this book, it even describes not reporting reliability, but reporting conditional standard error of measurement. Because there's no one reliability. So one, like if I were to give you, I could give you coefficient alpha for the same exam that gave me this curve, but that wouldn't really characterize maybe anybody on that curve, right? Because each person has a little bit different reliability. Am I making sense? Okay. What's this right here? Test information. So this is how adaptive tests actually work, by the way. How many of you have taken an adaptive test before? No? Yeah? An adaptive test will give you, it's usually run with IRT. Every time you take an item, it will go and give you a new update as to where it thinks your theta is on the backside. And then based on where your theta is, let's go up here, right? It says, let's imagine it gives you your first item and you're at -1 here. It will go, actually, go back to this spot right here. Gives you the first item. Your theta is, you answer it incorrectly. Maybe your theta was estimated to be -1. It would have to choose, let's say, between these 2 items and maybe the blue items that you don't see here. It would probably pick the most informative item at -1 and give you that one. And then you'd answer that. If you answer it correctly, maybe you move up to 0. Okay, it's going to give you the most informative item near 0. What that ends up doing is shortens the test length for you, because highly informative items are what drives reliability for what you do. All right. Okay, so finally, the last thing left here is if the IRT model fits the scale, the scale of the latent variables linear or interval. And that is that for now. Let's see how we do it in Lavon. Any questions on the theory part? Should we do, because I want to jump into the data, the two sides of my equation. All right, let's go see Lavon. And for this right now, I think I'm just going to grab my HTML file here and show how this works. So this is an example. Can you see this okay? Example of Lisa data. If you've got older adults, that's usually her data. You've got ed measurement stuff, that's usually mine. That she's got 635 older adults between the ages of 80 and 100, answering 7 items on this instrumental activities of daily living. Basically, can you do housework? Can you make your bed? Can you cook? Can you shop? Everyday shopping? Can you get to places outside of walking distance? Can you handle banking? And can you use the telephone? These are all yes/no items. Okay. Bring the data in. Turns out this is how to do it in MERT. I want to get down to Lavon though. Excuse me. Okay. So turns out, and this is me skipping all of lecture B, when you switch to categorical data, maximum likelihood for estimation for this is really difficult. Do you remember in CFA, we had the black box, and I said, it's magic, right? And what I was challenging you to think about was the idea that how can we, if CFA is like doing linear regression, but you forgot to observe X, how do we get the parameters? And my answer to that was, oh, look, we can write the likelihood function without F in it. So therefore, we can solve for these parameters and then go backwards and find F later if we need it. We can't do that with binary data. In fact, we can't do that with anything but the normal distribution. At least not that I'm aware of, or that I'm aware that we've discovered yet. Let's put it that way. So what that means is if we were to do full maximum likelihood on IRT, we would have to get a likelihood function that didn't have our latent variables in it, we would have to do something called numeric integration. We'd have to integrate across the range of the latent variable. There is no way we can do that in a tractable sense, like with one closed form equation. So that means every step of computation, we're sort of approximating an integral using a sum. If all that sounds confusing to you, you're right, it is. It's hard, and it takes a long time. But the part of this example above where it says estimation in Lavon is maximum likelihood using the MERT package. You're welcome to use that if you like. To keep class on track, we're going to stay in Lavon land. And that is actually what a contribution from item factor analysis gave us. So maximum likelihood sort of was really applied in, you see it in factor analysis, but then people quickly realized you couldn't do that with latent variables. Maximum likelihood did show up in IRT first, though, particularly once we get to the 1980s. But in factor analysis here with Lavon, in factor analysis, there was another branch for item factor analysis that looked into something called limited information. And what happened was, this is a group in the early 70s, Christofferson and then Bank Mutane being the founder and original developer of M+. Basically said, at the time, in Lizral, factor analysis, we could do a CFA with just a correlation matrix, right? Because if you remember, there was this crazy likelihood that we could build around a correlation if it was multivariate normal. So they thought, wait a minute, if we can do CFA on a correlation matrix, if I get a correlation matrix for binary data, could I do CFA on binary data with it? And the answer is yes. So limited information estimation doesn't use a Pearson correlation, it uses something called a tetrachoric correlation. You should know the main difference between the two is tetrachoric correlation is unbounded for binary data. A Pearson correlation with 0 and 1 data for the two variables has an upper limit that may not be -1. It's higher than -1 and lower than 1 unless the marginal proportions are both equal to 0.5, right? It's this crazy part where the correlation has a smaller range. So what this limited information method does is it estimates a factor analysis on a tetrachoric correlation matrix. But you don't have to give it the tetra, it'll figure all that out as it does its work. Okay? So Lavon, limited information only. That's where we're going to stay there. Turns out limited information is nice because when you do the factor analysis on the correlation matrix, you don't have to take the numeric integrate. You don't have to do numerical integration. You don't have to take an integral. It is literally being able to write a likelihood without the factoring. Asymptotically, given some of the ways that Lavon the theory works, you should get pretty consistent results between the two methods as n goes up. But the big difference is for limited information, again, you're just using that correlation matrix, whereas in what we call the opposite, what I called maximal likelihood before, it's now called full information, you're using the pattern of zeros and ones in the responses, right? Plus you're doing a little bit more integration. Okay? Okay. So the limited information version of this uses a probit model. And you'll often see this acronym, WLSMV, which stands for weighted least squares mean invariance transformation. I don't know why they didn't put a T at the end of that, but that's what it means. It is a version of a robust statistic to look at your model fit effectively, your fit function. Basically, standardizes your fit function to account for some of the issues in estimation we have. The model syntax is almost the same, though. If you wanted to define a latent variable, it's equal tilde. Remember that? And then you put your observed variables with a plus in between. What did I say last time, though? I don't like this. This is not the sum of those items. It's shorthand. Okay? If you want to refer to thresholds ever, you actually have to use a little bit different syntax. So let me get back up. When you do this, let me come back to this in just a bit. This describes the discrimination loading parameters. And then there was that other term. I called it an intercept right here. This, come on now. Give me my pencil, please. There we go. This right here is your intercept, item intercept. Turns out, negative mu, sometimes called tau, is a threshold. So what is going on here is the following. When you have a binary piece of data, because of that symmetry of the logit to probability, if you model the probability of 1 and you get an intercept, and let's say you then go recode your data so 1 is a 0. Right? So you basically flipped everybody's sign around and you model your data again, that intercept is negative, but the same value. Right? If it's mu when you're modeling a 1, it's negative mu when you're modeling a 0. So what's happening in Lavon and M plus is they're modeling the probability of a 0, not a 1. And what results from that is a threshold and not an intercept. So it's a slight change, but it will not make a big difference in what we do. But we have to denote it a little bit differently with our syntax if we want to refer to it. So the first threshold for DIA item 1 has the name of the item, the pipe character, and the name that you're going to give a label to it for the threshold. You all right? Yeah. Of course. You got you sick? Oh, no. There's a story there, but I'm not going to talk about it. So here, similarly, just like in factor analysis, when you're using limited information, you can do things like have a residual covariance. Because the the correlation matrix effectively that's there. How are we doing, everybody? This is pretty dry stuff, isn't it? I feel like I'm not really doing a good job today. What can I do to make this more informative for you? Nothing. Yeah.
Interpreting the results. I'm trying to figure out.
Let's do that. Let's do that. Okay. So here's your syntax for Lavon. If you want to submit it, let me I'll be going to submit. The only difference in submission to Lavon is this ordered statement. So the option ordered tells Lavon each one of the names of the variables afterwards are categorical. And when Lavon sees that, it treats this as if it were a item factor analysis, switches it automatically to do the estimation for it. So literally, if you don't include this line right here, it's fine. You can just run this model and get what you need. Yes?
So whether or not like 2 categories or 10 categories, and the Lavon does not care. It's just category.
That's right. Now, I will say the one thing about this is, well, we'll get to multi-categories in just a bit.
Well, yeah,
Yep.
I just figured you would basically changing our command based upon number of categories.
That's right. Okay, here we go. Ready? We get our results. Let's see what's the same. Remember the last time? Model test user model. This is like that overall test statistic that you had before. Now, it's based on different numbers. The way it works is a little bit differently because we don't have a log likelihood that comes out of our test statistic. So this is a version of the likelihood ratio test that comes from this estimation process itself, this diagonally weighted least squares in Lavon, or WLSMV in M+. But again, the way we'd interpret this is overall, this is like an overall model test of the alternative model, which is the model where all correlations are estimated simultaneously by themselves, versus yours, which is your model's implied version of the correlation matrix. This number here tells you whether or not your model fits the same as the saturated model. It does not, but that's normal. Then we get to the model test baseline model. This model is still what you had before. Baseline model is your independence model. This is the saturated versus the independence model. Right? So saturated meaning all correlations are estimated, independence meaning all correlations are zero. This test statistic tells you the 21 correlations that should be in the data, at least one of them is not zero. Right? How are we doing so far? That seems familiar, I hope? Okay. This is why we're staying with Lavon, by the way, okay, because it's going to stay the same. Have you seen the CFI and TLI before? They're formed based on the baseline model versus yours. The numbers are interpreted a little bit differently, although most people don't know that, so we're just going to save this. There are recent papers that say you should be a little more stringent in your model fit for this. This, by the way, the CFI TLI, are enabled because of the assumptions that are based on the limited information estimate. So you have to work extra hard to get these in Lavon. In MERT, the maximum likelihood version. So we're saying here that they look very familiar. So you'd say probably doesn't fit great. Then we get down to RMSEA or the robust RMSEA, and there's some wide differences between these numbers, which is kind of hard to explain. In one case, it fits well, and the other it doesn't. So which one do you pick? The good fitting one, of course. I say that tongue in cheek, but it's probably what people would do. Yeah, no, I like the robust better. This is actually one of the weird things about model fit that looks the same in categorical data, but in practice it works a little different. And I don't know that there's great guidance right now in the field for how to look at it, apart from you really want more stringent model fit. But when you see two numbers that diverge this high, it's because of the differences in how these are actually formed. I'm not sure. I'm not entirely sure. So, yeah, that would make a huge difference. Agreed. But standardized, so we can just keep going. The standardized mean squared residual, same that we saw before. And now finally, let's get into our parameter estimates, shall we? Okay, so here, each of these, so Lavon does not use the discrimination difficulty parameterization. So the loadings, the latent variables, this right here, these will be factor loadings, we would call them that, although they would be equal to discrimination. And here, each of these represents what? right? It is, going back to my,
Distribution.
it is the number of logits that go up for every 1 unit of F going up, right? So we just look at that like a standard value. Here, we'd see, DIA4 has the strongest loading. So if we were to plot its shape, which we'll have a little bit later after break, its ogive would be more steep, whereas DIA7, 1.5, should be a little bit more shallow. All right? Questions? Okay. The residual covariance, that's hard to interpret, but it's the same idea. This is sort of what else between two items, how additionally they are correlated or not. In this case, the p-value is bigger than 0.05 if 0.05 is your preferred cutoff. It says maybe there might be a correlation there, but it's marginally, it's hard to tell. We get down into the intercept for the factor. You'll note this is set to 0. You don't see a standard error or a z or p-value. That means it was fixed by me. So I identified it with a standardized mean for the factor of 0. I realize we're at break. Shall I finish this and get to break after that? Is that okay? Just be a couple more minutes. And then we get into thresholds. Each of these is now the reverse of the intercept. And which drives me crazy because I only think in intercepts, right? But that's just -1 times each of these, right? So as the intercept, what we know that to be is it's the expected logit when theta is 0, right? If you think of the equation right here, sorry for this right here. There. Clear out that. There we go. When f, or theta, the latent variable, is 0, the expected logit is mu, right? The logit of the correct response. That's on the intercept parameterization, so you have to think about this as, that's a 2, not a negative, right? Multiply these by -1. So that would tell you what? It would tell us where we know the intercept, f being 0, or factor being 0, is the mean. So we think an average person on our scale, that right there gives us their -1 times this is the log odds of a correct response for someone who's at that mean. Right? So it's a few steps extra. Now, what's that mean in terms of probability? Well, I don't have the logit the probability calculator in my head too much, but I do know this, that one of those is at 2.95. Right? And that logit scale, 0.9 was like 2.2, right? Oh, 4.6, excuse me. 2. Yeah. 99 is 4.6. 0.9, I think, is 2.2. But here, I don't have R up, but yes. So this one means the average person has a really big chance of answering that item correct. Whereas if you flip this one around, which is real close to 1, not as much, right? Or 1.1 right here, right? How are we doing? Does that make sense? So if we were to order these by difficulty, right, we multiply these by -1, the biggest number is the hardest. Or if you want to think about it on thresholds without multiplying this by -1, the smallest number represents the hardest item, or the one that has, sorry, not the hardest, the easiest. Yeah. All right. Then we get into a few other things. Scales are weird. These are things that has to happen in a limited information case. We don't put a lot of weight into them. So long as you use, when you estimate this, this option. There's 2 options of estimating this. If you estimate the parameterization equals theta, leave it like that. If you find yourself in a case where you don't need that, come talk to me. Email me, hunt me down, you'll know where to find me on YouTube. And then finally, we'll get a chance to look at R squared here as well for each of these. What you'll see, interestingly, under variances, they're all 1. No, I didn't. So it turns out the factor variance I did. But each of the item variants has to be 1 because it's a probit. It's fixed.
Because it's a C-score.
It's because the link function itself leads to a constant variance. Because these items are binary, you can't have a variance and a mean. And this part's taking care of the mean, so this has to be a constant. That's how it's working out. All right. I'm going to pause there. Come back in 10 minutes. 2:33, not 3:33. I won't be here. And I will be actually just a little 3:35, right about there, and then we will resume the fun. Thanks. Okay. Questions on the results of this point? Okay. So yes, question.
So if you go to the top, right there. No, wait, no, sorry, one more. Right there, with our estimates. That's where, if we had a rush of all the city,
They would all be equal.
you fit them like all with it, like X, whatever.
You would make a constraint across all the loadings. Yep, that's exactly it.
All right, thank you.
Great question. Like when we bro, I sound like my 10-year-old. Um,
I expect that.
bro, remember? Yeah, I do. I try to on occasion. It's usually playing. He's into an iPad game, so we play at night. Brawl Stars. I've seen Brawl Stars before. Like, sure, Hugh, let's play. We'll play a little bit, and I would tell you of the video games he's brought to me, I'm not bothered by that the most. So it's been pretty good. So I'm going to give you a yeah. It's honest. It's kind of weird. It's very the game like it's multiplayer, but it's really quick games. And then there's a bunch of like rewards. It seems like you're playing a slot like it's a slot machine for kids, which is like no, like no. But if you think of the experience, I don't know if you've gambled. If you haven't, don't. But if you've ever gone to a slot machine, you know, it's nothing but noise and anything that'll attract your visual field so you can't look away. Like it's like Medusa of our times, right? It's designed to like get your attention and keep it. And there's noise and there's movement and that's all of that in between the action. Like the game action itself is kind of boring, but then when you're done, it's like you get coins and you get this and you get an upgrade. And there's all these characters. It's like it's built for the 10-year-olds who need to customize everything. One last anecdote and then I'll quit. Like he likes playing video games, so we have this birthday party a lot where the 12 however many 10-year-old boys this time, right, playing Smash Brothers, and I swear they spend more time getting their characters the right outfit, the right color, and then they play for like 30 seconds and they spend another 10 minutes trying to figure. I'm like, guys, like, do you like the playing? Well, no, we like all of it. Okay, that's just I got to remember that's just when I was that age, we didn't have those options. It was not the same. Anyway, going back to what I was saying on this note, if you remember, bro, back when I was teaching CFA, that after we got through the model, we had to establish model fit. The first place we looked were the raw residual covariance matrix. In our data, because we're using the tetrachoric correlation, you'll look at these numbers don't quite look the same size, right? And that's because when we treat the data as continuous, covariances are not bounded, but correlations are, right? So these correlations are between 0 and 1, so their difference has to be between 0 and 1. So don't let it fool you. When you see this in CFA, you're like, I'm doing really well. It's not quite the same in IRT with the other value, the categorical data. The other thing we can look at is modification indices. You remember looking at these before. These are all the modification indices sorted by how big the index value is. Just like in CFA, this represents the MI column represents sort of the difference in chi-square if you were to add that parameter. So what this is telling us, if you look down here to the left side, DIA double tilde DIA 3 double tilde DIA 5 gives us the residual covariance between item 3 and item 5. That is the highest modification index. That value is 10.280. So would that chi-square look like that? Now this is a chi-square, so the chi-square distribution has a critical value at 3.84, that's alpha 0.05, if you're into that. But remember what I said about adding residual covariances in a measurement model. It violates a really fundamental assumption of measurement, which is, you know what I'm going to say? Right?
It undermines the one latent factor.
That's right. If you think of it this way, it does, but I'm just going to have to say it one more time. the reason why DIAA3 and DIAA5 are correlated, there's three versions of it from basic stat. 3 causes 5, 5 causes 3, or something else causes both of them at the same time. Our measurement model is the something else causing both of them. And so if we add a residual covariance, we're saying, no, actually, it's not just the measurement model causing these to be correlated. There's something else wrong, something else out there. So when we call this scale, the adult daily living scale, whatever, if we add a residual covariance, it's like saying it's adult daily living in other things as well, too. Right? Does that make sense?
At what point would you consider a second latent query if you see something like that?
I would consider it now. Actually, I wouldn't see that. I would consider it by looking at this model fit statistics here, right? But I'm going to press forward with the example just to give us what we have here. But yeah, I would like the modification index to me is not as relevant as like model fit. And really, the hard part is disentangling where the misfit is, right? We've got 3 and 5, 1 and 3. Okay, so 3 is common to both of those. But then 4 and 5, which 4 and 5 are common to both. So I'm like, okay, I'm trying to think of where we'd put another factor.
Like almost like making a closed loop, so to speak.
Yes. Yeah. Yeah. So here it again, 3 and 5, 1 and 3. And these are in different dimensions. Like we overestimate versus underestimate, each of these. So it's really hard off of this to tell where that would go. So here's a fun now version of psychometrics, like now as in the last 10 years. There's a field of psychometrics called network psychometrics. I don't know if you've heard this before.
Like network theory, like spread ideas.
Sort of like that, like social network analysis applied to psychometric data. Executive mode means I can't see it. So sorry, I get freaked out about technology. This is one of my personal shortcomings. I have to apologize to you all. Like technology, I just get so irrationally angry with it, and I just yell, and it loses all focus. Anyway, here's how it works. Network psychometrics. This is an example of it. The network psychometrics itself does not look for latent variables. It takes what's like a matrix of partial correlations or semi-partial correlations, and it tries to see which items are closest, are most heavily related to each other. So it's hard to tell with this graph when you get too many items in a graph. But if you were to look, compare and contrast, there's a pretty famous image from, if you were to generate IRT data with this, and I don't know that I can, let me see if, give me just 1 second. I have the image in a presentation I just gave at SMEP, actually. So, SMEP, experimental psychology. And here was the presentation. Actually, this is Jacinta Olson's dissertation she's working on, but we worked sort of out there. And Iowa for a limited time. This is the graph I was really trying to show you. If you generate this right here, if you think of the big circle is a latent variable, and you generate this, and maybe there's some little correlation. What this works out to be in a network sense, if you model it with respect to each of these paths right here, are a sort of a semi-partial correlation between the items. What you want to then do is cluster those. Why I'm saying this to you is like what you're getting into there. We're getting into exploratory analyses, and it's really hard to easily do that with what we've seen in the data that I just had. But this is another way of doing it. Network psychometrics is fun. Love to teach a class on it. Probably never will. There. And I think I just closed even the lecture too. Or did I? No, it wasn't lecture I was doing this. Okay. Promise I'm still here. You're not seeming like it. Okay. Questions? Analysis questions. Should we look at the plots of item characteristic curves? There we go. Uh-oh. Hang on one second here. Why is my plot not showing everything? What's that? All right, give me a second. I thought I had I'm going to go back in time to where I made this example many years ago. You are now on a time machine. And somehow an example itself didn't quite come through. Well, I guess this is for one item. Okay, I have that. Wanted to show for all, but that's okay. So this is item 2. Item 2, when we look at the item itself, item 2 had a loading of 2.626 and a threshold of negative 2.803. So if we look at the item characteristic curve, take a look at, so it's hard to tell what the loading is here, but I think we can sort of see it. These are our probabilities. So loadings aren't our probabilities, right? Loadings are in logits, right? But what you can see instead is where the intercept is. So what you have to remember is when the logit is 0.5, that's where the linear predictor is 0, right? So this is 0 when the factor is 0. We discussed that kind of before, right? So if we actually, no, that's not true either. Excuse me. I'm doing this wrong. Okay, negative 2. I totally switched parameterizations there on you. Let's do that one more time. Negative 2.808 is the expected value for the probability of a 0 when the factor is equal to 0. Otherwise, what you have to do is, when the factor is equal to 0, look at that probability. It's very close to 1. That's where the negative 1 comes in, right? This is the probability of a 1. Right? That negative 2.8 for a threshold is really 2.8 for an intercept. And the logit of a 2.8 is very close to 1 at 0, is what we're trying to say here. So it's really hard to see the connection between the two. What I was jumping into was the discrimination difficulty language. And I apologize for that. Seems like that seems to be second hand for me, even though my PhD is in psychology. Do a lot of work in educational measurement. If we were to figure out where the difficulty is, you can almost draw a line down to where it would be, right? It would be just a little bit bigger than negative 1, where 50-50 is. How are we doing? If I wanted to convert to discrimination difficulty, these are a little bit easier to recognize, especially difficulty. There's that difficulty value right there, negative 1.067. Okay. Any other questions on this abbreviated version of this lecture that Lisa gave a better job of? If you want more of this, go back to her videos. This is me just getting us reminded. Next, the questions I should ask. Any other questions? Yes.
Conceptual difference between, or like how to apply difficulty and discrimination when it's like a behavioral measure.
They're the same, right?
But like that's not the right answer.
Oh, you just say that endorsing a 1. So it's the probability of a response of 1 is what you're saying. So whatever that language means, and again, education is correct response. In this, it's able to do the activity, right?
And this is just for
Binary data.
Okay, I'm sorry. I was thinking about.
We're about to get to categorical. That's next. Any other?
I'll wait patiently.
No problem. By the way, here's all the other item characteristic curves for each of these items. This is from MERT, though. These are estimated from MERT. I wish they were superimposed. I didn't do that in my plot, so sorry about that. But there you see. They do look very similar. In fact, if you wanted to look at their loadings here, there's quite a range. I don't think a Roche model would fit it as well. But Certainly similar when it comes to where their thresholds are. About the same range there, too. Okay. Shall we move forward? Okay. Now what we're going to do is talk about what happens when the data have more than one category. And for that, I have another lecturer. Used with permission from Lisa Hoffman, of course. Okay. So now what we end up doing, I'm only going to talk about one of these models in the interest of time, because that's the one Levon implements. It's the graded response. It turns out when you go from a binary item where there's only two options to a multi-category item, which we will also call a polytomous item. Polytomous being more than two categories. Dichotomous, by the way, is a two category. You may hear that term as well. Binary is much more specific. Binary is a dichotomous item that is 0 and 1, right? So all binary things are dichotomous, but all dichotomous things aren't necessarily binary, right? But for this, we'll call it polytomous or ordered categories. This comes out of her "Too Legit to Quit." Yes, I know. That's her joke. All right, that's hers.
And it's objectively funny. Just saying.
So let's just gender stereotypes, right? If this guy were to say that, yeah, someone would say dad joke, boomer, yada yada yada. But women can get away with that. That's what I'm saying. That's what it feels like. Okay. No, I would like throw music in my slides just because I wanted the music there, but I'm trying to keep the pun away. But yes. So when you have more than one category, the issue is this: you come up with submodels. Okay? This is the weird part. So instead of having one overall item response function, what we model with categorical data is what's called a cumulative logit or proportional odds. It depends on which field you're in of statistics or biostats or epidemiology even. Here, what we look at is, let's imagine we have 4 possible responses. We'll just code them in the computer 0, 1, 2, 3. Let's further assume they're ordered, meaning a 3 means you are endorsing the item more than a 0. Do you see the difference? It could be different if you said these are nominal categories. Right. So this is like a Likert scale. Likert type items tend to be are definitely in ordered, right? I'm out of agreement. Yeah. So I'm making a distinction because other models don't assume the ordering. So we have to assume ordering for this to be the case. When that's the case, if we have 4 categories, we'll have 3 basically binary IRT models. I put in quotes. They're submodels. They are models that model the probability of the response being greater than a 0, being greater than a 1, or being greater than a 2. Okay? These are cumulative. Instead of saying the probability of y equals 1, which was the binary version, it's probability of y greater than 0. Now you'll note, if you have a binary item, what I just said is equivalent. Right? So what this is doing is generalizing this logistic process to accommodate more than one mean per item. It's a mean. Here, the expected value is the probability someone's at each of these different categories. Okay? So far, so good? So here, the other part of it is in the model itself. If we were to build an empty model to this, something without a predictor, what we need to have is each one of these submodels will have an intercept. Those intercepts will also be ordered in reverse order of the categories. By the way, I will. Yes. So here, furthermore, each of these intercepts is unique to the submodel. So when we have 4 categories, we have 3 intercepts. But for any of the predictors, there's only one slope. So the slope is held constant across each of these models. How are we doing with that? For each item, that's right.
Okay.
So within an item, we have these multiple, basically cumulative models. Be right there. Within each model, item, we have cumulative models. These are with respect to this one item itself. The slope for that item will be the same on each of these submodels. But then for the next item, it'll have a different slope, but it'll be the same on its items submodels. Yes. No. Okay. Other questions? Okay. And of course, logit intercept is 1, threshold is the opposite. If you want the actual probability of whether a person picks a 0, 1, 2, or 3, you have to do some subtracting. Okay? Right? So if in the case of the intercept version of the model, right? Now, remember, a threshold goes the opposite direction. But in case of the intercept, the probability of a 0 is really the probability of it's 1 because you can't actually respond below a 0, right? Minus the probability of being at 1 or greater. So, right? Or 0 or greater. Or, excuse me. Going back to this right here. The first submodel is the probability of being greater than 0, right? Or so that's a 1 minus the probability of being greater than 0, which means 1 or higher. Right? So probability of a 1 compares the probability of being 1 or higher with the probability of being 2 or higher, and so forth. And so what you end up getting is a set of probabilities. So conditional on a person's latent variable value, you'll have a probability they picked each category. Those probabilities will sum to 1 as you would expect it to do. Okay? So if you were to give a quick summary, because we don't have a lot of time, but I want you to work on this for your next assignment, so we'll get to that, and we'll have more time to talk about it as we go through. But if you wanted a quick summary of this, if your data had multiple categories, or if you had 2 categories, Lavon works the same way. What's different is the output, right? In Lavon, you'll have a lot more intercepts or thresholds, right? But in binary data, you'll just have 1 threshold, right? And it's nice, you don't have to tell Lavon how many categories you have in your data. It will do it for you. But the categories must be ordered. They will do an integer ordering. 0 is less than 1, 1 is less than 2. Questions on any of that so far? Okay, really quick, this is probably things you won't ever pay attention to, but the PDF or the probability mass function is simply the probability, the actual probability a person's equal to that category raised to whether or not they were at that category. So if you give a response of a 3, this indicator function right here would be a 1, and these other ones would be 0. This function is basically, is the thing in the brackets true? Give a 1. If it's not, give it a 0. Anything raised to the 0 power becomes a 1. You're left with just that probability for the probability mass function. That is what we call a one-trial multinomial distribution, otherwise sometimes referred to as a categorical distribution. That is one way of looking at the data. This distribution applies regardless of the type of categorical data we're putting in, so long as the set of categories has a finite number, right? So you will see, if I go back to the beginning of these slides, these names: graded response, partial credit, nominal response. All these make a little bit different assumption on how we get our probability of a correct response. Graded response says there's an ordered process. This says there's sort of an ordered process, and this says there's no ordered process, but they all use a multinomial distribution. Okay? Okay. I'm going to move up a little bit quickly here. So the item factor analysis, this proportional odds model that I was just describing is called the graded response model. Even in psychology, people use that term. Even in social science, dates to 68, I want to say, Samajima, Fujiko, or maybe 71. She did a number of, 71, I think it was. 68, 68. It's been a while. Anyway, don't test me. Don't test me. That right there is the 3 submodels for the 4 category item. You can see each has negative threshold, which really means intercept, right? But still have your loading times factor. So basically you've done what you did with binary data but expanded it. This looks like 3 items with a Roche model, but this is the 3 submodels, right? And what this pink line right here represents is the probability of being a 1 or higher, the cumulative. This yellow line is the probability of being a 2 or higher, and the blue line is the probability of being a 3 or higher. Right? You can see I'm changing the way these are said. Greater than 0, greater than 1, greater than 2. Some of us think about it slightly differently. So here's how we want to think about it, though. Let's take a look at theta of 0, right? A person with a theta of 0, if you want to say what's their probability of being greater than 0 on the response, it's 9. So they have a 90% chance of answering a 1, 2, or 3. What's their probability of answering a 0? 1 minus it, right? So it's that region right there, or like 0.08, right? So then we get to the yellow line. That's their probability of being answering with a 2 or a 3. So what's their probability of answering a 1? It's the difference between the pink and the yellow, right? And we can keep going on and on so long as you realize that for any given theta, the whole range gives you the value probability of 1, and the lines segment it to tell you the probability for each category. Does that make sense? So then there's another way of drawing this graph. It looks like this.
That's with our probits, yes.
Yes. No, this is not with probits. So the previous slide were the submodels, which was the cumulative response. This is not submodel. This is the exact response. So this blue line looks the probability y is equal to 0. Right? The pink is the probability the y is equal to 1, equal to 2, and equal to 3. Do you see the distinction? Right? I find when I look at data that the cumulative lines don't do me a lot of good. But this right here tells me a lot. And we're going to see that in just a moment when we get to the data. In that, a lot of times in real data, you'll have categories that aren't selected a whole lot in your data set. So you'll see that this probability for them will almost be lower. It will not be a maximum for any point of theta at all. Right? That's something to note. You can see how close to or how spread out each of the thresholds happen to be as well too. So right here, for instance, this looks like real data right there. Right? This is where, okay, what is this telling us? A person whose theta is below 0 is likely to pick the 0 category all the way up to where you get to 0. And then it flips a person with never mind. Not a person with a theta of 0. For any value of theta, for theta values between -4 and 0, the most probable response is selecting y equals 0 for that item. And then once theta gets bigger than 0, once the latent variable is above its mean on a standardized variable, the most likely probability is for the highest category. That doesn't mean people aren't selecting these other categories. It just means their probability is much lower. Okay?
And those actually all really well is sort of curricular seem like part of it.
The reason for this is because the parallel nature of the lines, right? This right here, right? So it's parallel, and then complementary, right? Basically. When you get to other models where it's not like that, which I'm not going to go into, you'll get a little bit different looking. But I'm going to stop there for the theory part. Questions on the theory? So in summary, what did we talk about? A graded response model is what we do for properly treating like Likert data. Let's just say that. And it's like the binary model, but it has more thresholds. It has one threshold for every category minus one for each item. Okay? Should we go to the example and how we do it in Lavon? Because this is going to go a little quick too, in parts. I'm trying to like streamline the information a bit too. I feel like it's a lot of information overload. That's not what I wanted. Come on, Jonathan. Okay, in Lavon, I'm giving you the shorthand syntax now. The syntax is the same. This is for a data set with the same instrumental activities of daily living. I just call it a little bit different here. CIA instead of DIA items. Oh, I get it. The DIA were dichotomous. These were the categorical. There were multi-categories. And each item had 4 categories. Can't do it, big problems, some problems, and no problems. All right? So they're ordered in it. So the Lavon syntax, to specify the model and to run it, is identical to 2 categories. So I don't need to spend a whole lot of time on that. But you know what? This is disappointing. I'm disappointed because I feel like I'm missing a picture that I thought I worked on this morning. But let me just double check. There it is, yeah. This is from the previous time I taught the class. I apologize. I can try to update mine, and I will update the link when I'm done. But here is the output that you see in Lavon. And again, it's going to look almost identical. Almost identical to what you saw in IRT. So the model fit is the same. Right? You get the one loading per item, once again, if it measures one thing. And again, we talk about how well those loadings work. And again, the thing I forgot to mention is because these are loadings, they're like interpreted the same way we like to interpret them in factor analysis. This is like the bigger value here. It's the stronger relation between the item and the trait itself, right? But then for each item, you'll note we have 3 thresholds, right? So you'll see each item listed 3 times: threshold 1, threshold 2, and threshold 3. Yes.
If you have, like, let's say one of your questions had like 5 categories
Mm-hmm.
of the 10 3,
It would be.
then that one would have more than the other.
Exactly. It would be automatic.
But it would just show up.
It would just show up. And that's why I'm trying to streamline this to just focus on it. Yep. It would just show up. So let's do some interpretation of those items. We can look at here's model fit. I really want to look at the item plots here. So this item plot is the second item. Okay. So what do we see on the second item? The second item is, sorry for the scroll, bed making. So can't do it, big problems, some problems, or no problems. So the 0 point looks like the most likely response for an average person is no problems, the high end of the scale, right? So what we like to think about for interpreting this is at what point on the ability continuum or the daily living scale continuum, where do we start to see big problems become the predominant, or can't do it become the predominant feature? So you can envision this scale being given out to elderly folks who may be considering whether they can live on their own or need some assistance with living. So if you think about that here, what we want to look for here is, remember, the line that's at the top is the category that is most likely to be picked, right? The sum of each of the points of the line sum to 1, but for a given region of that. So what we would say is between theta is below, all the way down below where this red line becomes equal to the blue here. So right about negative 1.5. So negative 1.5 standard deviations below the mean is where people stop being able to make the bed, right? And then we get into a region. You'll see this green option, which was some few problems. So can't do it. Big problems, some problems, and no problems. So big problems comes next. You'll see there's never a case where big problems is the most likely category chosen, but it's the closest to it right here about that 1.5 standard deviations below the mean. At 1.5 standard deviations below the mean, it's almost like a toss-up between can't do it, big problems, and some problems. But then between negative 1.5 standard deviations and where the blue line is the peak up until just above negative 1 standard deviations is some problems making the bed. But then shortly after that, so a little above 1 standard deviation below the mean is where you'll see can make the bed happens. So when you're looking at how to interpret this here, if you think of the population of people, folks between 80 and 100 years old, you would say, okay, we're trying to understand what it means to have a scale number there. Where you want to see potential sources of where people need help in this situation is somewhere between 1 and 1.5 standard deviations below average, right? How's that sentence? Make sense? How we doing? Okay, questions. So what do we do with this? Here's why I'm giving you the abbreviated version. I mentioned at the beginning of class, the next homework is your data analysis, and then we work on that. I'm expecting you to work with me on data analysis to help you. This is where I'm trying to transfer practice from theoretical examples to things that's supposed to be hopefully a little bit more meaningful to you. I'd love for many of your scales are Likert or binary items. Am I right? Does anybody have anything other than a Likert or binary? Okay, that's good. That's what I thought. That's what I thought. I read every one of your proposals or your list of your data. So that next one will be to apply this IRT perspective. If you have binary data, I know, Michael, you do, it would be the binary case, but the code would be the same. If you have Likert data, it would be the categorical case or the greater response case. And again, in either way, ordered equals is the way it works. But why I'm saying that is if you think of structural equation modeling and you think of I keep going back to it, but I like repetition, it makes it easy. If you remember our very first, there they go. Our very first example where we had marital happiness being predicted by, happiness being predicted by marital status, where when you didn't do the structural equation model, it looked like there was a significant effect of marital status on happiness. But if you did do it this way, it became non-significant, and I was like, this is not a theory. This is right. Try not to wade into something controversial, but as more gets your attention. If you think about it this way, if these items were categorical, what would change in our analysis? The syntax wouldn't change, right? The only thing that would change would be how we call Lavon to run the model, where we add the ordered statement. But the structural equation model and everything we interpret about it would still remain. So what I'm hoping to focus on with you in this analysis, we get to our next step, is that when you're thinking about your measurement model, your thought shouldn't be, I don't want to do IRT, that's too complicated. It should be, what's the most appropriate distribution for my observed data? And that's the question we ask in every measurement, every statistical data science context, right? And so when you do that, what I'm trying to build this lecture around, why I'm trying to abbreviate it, but also there's a lot of information in this IRT that you would normally get in a regular IRT class. I'm trying to streamline it just to make this parallel in structure to the CFA that we've done before, is that What changes is in the measurement model, these items are now treated as categorical. So you wouldn't see a residual variance down here, but everything else would be about the same. And so in structural equation modeling, when you have categorical data, you just tell Levon it's categorical. That's what I'm trying to get us to focus on here. And when you want to describe what that means, yeah, that's where we have to sort of take apart each item, maybe calculate some item characteristic curves. Some of the functions that I have on the website, on our website for today in our markdown file right here, you will see functions that you can use that will give you item plots if you just give it your output from Levon. Levon won't plot this for you, but I created functions to do it for you. So you should be able to even go and plot each item if you wanted to describe what the measurement model proportions are and what you do. Yes?
Can you provide data for this markdown file, not the actual data?
I don't know that I have simulated for it, though.
Okay.
But, yeah.
Because obviously.
No, but this is built in a way where you should be able to take your data and sort of, once you build a model, should be able to do it. Yep. It'll just be changing out the variable names. But what I'm trying to get to is the item plots themselves, which show up over in the old lecture, but for some reason not here. Why you do this is to sort of describe what's happening in each item in your measurement model, or to see that the model seems to be valid, right? Because that latent variable may not exist, or it may not exist in the way we think it is. But apart from all of this and the terminology, the purpose of structural equation modeling still exists, which is, are there mean differences? Better yet, go here. When I go to that slide toward the end, close your eyes if you don't like scrolling. When I go to this slide toward the end here, what this is really describing, this model, is basically, are there mean difference in the latent variable of happiness based on this categorical indicator of whether a person's married or not, right? Which happens almost all the time when we use these scales. So in the couple seconds we have left here, another indicator of where we're going, I'm trying to conceptualize IRT as replacing the measurement model but being appropriate for data. So the structural equation modeling premise still is there. But then now we're saying, hey, are there differences between groups? One of the next units, not next week, but the following week, we have to talk about when we go and look at this experience is to go and ask, are there mean differences? Turns out we need to also make sure that there's not mean differences on the items for this as well. It's something we call measurement invariance. So we're going to bring that along into our discussion as well too. So if you're thinking of the taxonomy, reverting into childhood language here, taxonomy of what we're doing, this fits into being a more appropriate model for our data right now. In the next couple of weeks, we're going to have a couple other measurement concepts that will come up. Next week, A-Kyung's lecture will be about not whether the data are categorical, but what if the trait is categorical? What if you're diagnosed or not? What if you're sick or not? That's next week's bit of lecture. And then the following part of that, I will describe higher order factor models. And then the week after that, I'll describe measurement invariance, which says how to do this to check for one big confound, which is this is assuming that there's no effect of marital relations on each of the items too. Because if you don't control for that, this gets contaminated. And then finally, we'll put it all together after break with doing the full structural equation modeling like you see in this slides. And I think my lecture actually takes this example and builds it more and for where we go. Okay? Does that help you kind of conceptualize where this fits in the big picture a little bit more? Again, this can be a whole semester-long course. Actually, at University of Kansas, Billy Skorupski, my good friend and old colleague, used to teach 2 semesters on item response theory alone, right? So depending on your field of specialty, it can really be deep. That's why other courses exist, but I'm teaching this in the context of more of a structural equation modeling, so I'm really just skimming a surface, all right? Okay, one last thing. Don't forget, next week please do turn in your, you can upload a file, Word. If you wanted to handwrite you can do that. Just take a picture and upload it. The upload up line is fine too. I can do either. I will read both. I will make sure. I'm hoping that this will help your grade. And again, just to know, thank you for coming back. Sorry for the experience of the exam. But I really do appreciate each of you. And none of you are going to fail the class at all. Okay? We're going to find a way where we're going to walk out and be proud that we're all here. All right? Thank you.